Welcome to Daily Papers, the podcast where we break down fascinating new research.
Today, we're venturing into the quantum world to talk about a hidden secret inside some of the most mysterious materials known to science. We're talking about tiny, invisible whirlpools of electricity.
And how scientists are using a technique that's basically atomic-scale pool to see them. This isn't just a fun science experiment. It could help solve the puzzle of high-temperature superconductivity, a holy grail of modern physics.
The paper we're looking at is a review titled Orbital Current Signature Using Neutron Diffraction by Dalila, Bounoua, and her colleagues. So let's start with the big picture, superconductors.
Right. Superconductors are materials that are, super at conducting electricity. They have absolutely zero electrical resistance. If you made a loop of superconducting wire and started a current in it, it would flow forever.
The possibilities are mind-boggling. Ultra-efficient power grids, incredibly powerful magnets for things like MRI machines or maglev trains, and super-fast computers. The catch has always been temperature. Superconductivity usually only works at temperatures near absolute zero, which is colder than deep space.
But then, scientists discovered so-called high-temperature superconductors. Now, high is relative. We're still talking incredibly cold, like minus 150 degrees Celsius. But the big mystery is that we don't fully understand how they work.
And a key part of that mystery is what happens just before they become superconducting. They enter this strange state of matter that scientists call the pseudogap phase. It's like a weird waiting room, and for decades, nobody could agree on what was actually happening inside.
This is where our paper comes in. It argues that the secret of the pseudogap is something called orbital loop currents. That sounds really cool, but what are they?
Okay, think about the atoms in a material. They all have electrons orbiting their nucleus. Usually, we think of these orbits as a bit of a cloud, but the theory of loop currents suggests that in these materials, the electrons get organized. They start flowing in tiny, coordinated loops between atoms.
So not just random electron clouds, but little synchronized whirlpools of electricity?
Exactly. And a fundamental rule of physics is that any moving electric charge creates a magnetic field. So if these microscopic whirlpools are real, they should produce a very faint, very specific magnetic pattern inside the material.
But how on earth do you detect a magnetic field that's generated by something so small and so weak? It's not like you can just use a compass.
You can't. You need a much sensitive tool. And that tool is called polarized neutron diffraction. It's a mouthful, so let's break it down.
First, you need neutrons, the particles in an atom that have no electric charge.
Right, but even though they're neutral, neutrons act like tiny spinning magnets. They have a property called spin. The polarized part just means the scientists use a clever trick to get all the neutrons in their beam spinning and pointing in the same direction, like a perfectly disciplined army of compass needles.
So you've got your army of tiny magnets. What's next?
You fire them at the material you want to study. When one of these neutrons flies past one of those tiny magnetic loop currents, its own magnetism gets nudged. It gets deflected, and sometimes its spin even gets flipped around.
So by seeing how the neutrons bounce off, or diffract, you can work backwards and map out the hidden magnetic landscape inside.
Precisely. And that's what the authors of this paper review. For over 20 years, they and others have been using this technique and finding the exact magnetic signature that you would expect if these loop currents were real.
So it's not just a theory anymore. They've actually seen the evidence for it.
The evidence is incredibly strong. They found a consistent magnetic pattern that can only be explained by these loops of current, and it appears right at the temperature where the mysterious pseudogap phase begins. This is the smoking gun they were looking for.
What's even more compelling is that this isn't a one-off fluke. The paper shows that these loop current signatures have been found in a whole family of different quantum materials, not just the famous copper oxide superconductors, but also materials called iridates and kagome metals.
It suggests that this isn't just a quirk of one material, but a fundamental behavior of electrons in these complex systems. The existence of these ordered circulating currents seems to be the key feature of the pseudogap. It's the missing link they were searching for.
So by solving the mystery of the pseudogap, we get a huge step closer to solving the bigger mystery of high-temperature superconductivity.
That's the hope. If we can truly understand how and why these currents form, we might be able to figure out how to control them. And if we can do that, maybe, just maybe, we can design new materials that are superconducting at much higher temperatures.
Even, dare we say, at room temperature. That would be a world-changing technology.
It's still a long way off, but this paper shows just how far we've come. It's a fantastic piece of scientific detective work, using a really clever tool to prove that a hidden, swirling dance of electrons is happening right under our noses.
A beautiful reminder that there's a whole universe of strange and wonderful physics happening at the atomic scale.
And a perfect place to leave it for today. Thanks for tuning in to Daily Papers.